Welcome back. At this point, we've seen a number of examples of recursion, and I think it's fair to say that it's not immediately obvious why we should care about recursion, because the iterative solutions looked at least as simple for most of the examples as the recursive solutions. But in addition to just being this is a powerful way to think about solving problems and computationally, it is going to, as you're going to see in a minute, turn out that there are some really interesting examples where recursion just solves problems so beautifully and so elegantly in a way that would be very difficult iteratively. And to show you just one example of that, we are going to talk about the game Towers of Hanoi. And if you're not familiar with the game, it's a very simple game. There are three sticks, and there are discs of varying size that form a pyramid or a tower. And your job is to move the discs from one peg to another peg. And there's a couple of simple rules. You can only lift one disc at a time, and you can never put a larger disc on top of a smaller disc. So that's a simple rule. And if I'm going to show you a couple of examples, but you can go read about Towers of Hanoi. But before we get into how to solve this, go ahead and watch this video. It's a video of me playing a version of Towers of Hanoi with 4 discs, and you'll get a sense of the rules and what I'm doing. And then we'll come back and talk about how we solve this recursively. Peg 1 to peg 2, well, there's no hard work here. You just simply pick up the disk and you drop it down. And the reason you can do that is you can pick up one disk, and as long as you're not putting that on top of something that's bigger, you're done. So the case with one disk is trivial. Okay, I think I probably stated the obvious at this point. Let's do the case with 2 disks. Your job is to move these two from peg 1 to peg 2. Well, okay, pretty obvious to do this. The small one obviously can't go here because then the big one wouldn't be able to go there. So we've got to move from 1 to 3. And at this point, now we're sort of done. We've cleared the area for 1 to move. 2 is free, so we simply move one disk from peg 1 to peg 2, and then we move 3 back to 2, and then the pyramid or the tower has moved from 1 to 2. So 2 is pretty easy too. Good, let's do 3. Okay, now at this point, what do we know? We know how to move 2 disks from one peg to another. I moved it from 1 to 2, right? And we know that. We move the small one over to here, we move number 2 over here, and we do this over here. And by the way, it doesn't matter which peg. So if I wanted to move 1, 2 to either 2 or 3, it's the same thing. If I wanted to move these 2 to the third peg, I would move 1 to here, 2 to here, and then 1 pops over, right? So it doesn't really matter which the final peg is. Well, okay, so if I want to move all 3, well, I already know how to move 2. So without going through the steps, let's just go ahead and move both of those over to here, okay, using the same technique that we just used on the previous slides. And at this point, I'm free to move 3 over to 2. And again, I've got to move 2 disks from one peg to another, but I know how to do that. We've already done that. We've already shown that you move the small one to the spare peg, we move the next one to where it wants to go, and then you move it back. And so I can just do that en masse, okay? And now you can sort of start to see where I'm going with this. You can think about solving a Towers of Hanoi with 3 disks as sort of solving 2 versions with 2 disks, and then just sliding that third disk over, and of course we're going to be able to scale that up. Okay, so let's do this now with a little bit of pseudocode, and then we'll actually write out the code. So let me just formalize what I just said. So I'm going to write a function, Hanoi, and it takes 3 parameters. How many disks? What is the start peg? And what is the final peg? So this says, please take 3 disks from peg 1 and move them to peg 2. Okay? Hanoi 312. Now, to do that, what do I need to do? Well, I know that I need to get 1 and 2 off of this number 3's back here. So I need to move 1 and 2 over to peg 3. Okay, well, what does that mean? Well, it means I want to solve Hanoi with 2 disks starting at peg 1 and moving to, not peg 2 of course, but to peg 3. So to solve this problem, what I'd like to do is to solve this problem first. take 2 disks from peg 1 to peg 3. How do I do that? It's recursive. Don't worry about it right now. We'll come back to it. And at this point, what am I free to do? I'm free to move that disk from 1 to 2. So let's go ahead and define another function called move, which is simply to actually perform an operation. So this Hanoi, as you're going to see in a little bit, is going to be the recursion, but the move is you're actually moving a disk at this point. So now I can move disk 3 from 1 to 2. Obviously, that's from 1 to 2 that comes up here. Now what do I have to do? Well, I've got to take these 2 disks and move them from 3 back to 2. How do I do that? Well, let's solve another Hanoi problem. What the start and the stop peg are doesn't really matter to me. So now I'm going to solve, please move 2 disks from peg 3 to peg 2. How do I do that? It's recursive. Don't worry about it. We'll get back to that in a little bit. Okay. Good. So let's now start to write out this code in Python. So I'm sorry, I changed the name of the function. It's now going to be called solve Hanoi. It takes 3 parameters. N, which is the total number of disks, okay? Start peg, end peg. So for example, on the last example, it was 3, 1, 2. Take 3 disks from peg 1 to peg 2. Okay, we're going to do this recursively, obviously. And so we have to think about the base case, and then we have to think about the recursive case. Although we've sort of seen the recursive case a little bit, and we've also seen the base case. The base case is that if you only have 1 disk. If you have 1 disk, that's a trivial problem, just move it. You have to move it from, if n is equal to 1, just go ahead and move that disk from here to here. Okay, so if n is 1, then move a disk from the start peg to the end peg. And what does it mean to move a disk? Well, I'm not going to go ahead and do all the graphics. So for move, I'm simply going to print out what is being done, what is the move, and then you can follow those instructions. So I'm going to print move disk. I'm going to print out the disk number from this peg to this peg. Okay, so I take these 3 numbers here, and I just print out an instruction that you can then see how this gets done. This backslash, by the way, is just because I've got a line continuity here, a line break. All right, so that's the easy part. Move this disk from here to here. Okay, good. Let's do the recursive part now. So if n is not 1, I have to do what? Well, I've got to get the top disks off my back, and I've got to move them to the spare peg, and then I've got to take that one big disk that's on the bottom, physically move it onto the end peg, and then take those remaining n-1 and then move them back. Sounds a lot like recursion, because solving towers of Hanoi with 3, 2, 1, it's all the same, right? It's the same rules, and since that bottom one is the big one, I can put anything on top of that, so there's no rules against moving anything there. So first thing first, we're going to have to figure out what the spare peg is. So if I want to move from, say, 1 to 2, what's the spare peg? 3. If I want to move from 1 to 3, what's the spare peg? 2. So for any start and stop end peg, I've got to be able to know what the spare peg is. Now I could write a conditional. I could say if start is 1 and end is 2, then spare is 3. If start is 1 and end is 3, then spare is 2, and so on and so forth. Or I can use this clever little equation here that says for any given start and end peg, the spare peg is 6 minus the difference between those. First of all, let's convince ourselves that that's right, and then let's ask why it's right. So if start is 1 and end is 2, that's 6 minus 1 minus 2, which is 3. Good. If start is 3 and end is 1, that's 4. 6 minus 4 is 2. And you can convince yourself for any start and end peg, this will be true. Why is this true, by the way? 3 plus 2 plus 1, of course, is 6. And so if I take the values associated with 2 of the pegs, the one remaining must be 6 minus whatever these values are. So it's a clever little trick to figure out the spare peg from these 2. All right, so now, and by the way, why do I need to know the spare peg? Well, when I move, if I want to move all 3 from, say, 1 to 3, I have to move 2 of the disks from 1 to the spare peg. So I'm going to have to be able to figure what that is for any pair of start and end. Good. Now let's go back to our recursive code. So here's my simple move disk. That's an instruction. Here's my base recursion case. And now I'm ready to go. So first things first, figure out what the spare peg is. It's 6 minus start minus end. Why do I want to know that? Well, because to solve Towers of Hanoi with 3 disks from start to end, I'm going to solve a simpler problem. There is my recursion. Solve Hanoi is solve Hanoi with n minus 1 disks. So that's the top of the thing, leaving the bottom one. From the start, obviously that's where they started, to not the end, but to the spare. So please solve for me. Take these n minus 1 disks off my back and put them onto the spare. How does that happen? Recursively. We'll walk through that in a minute. Once that's solved, trust that it's been solved, what do? Well, now I've got this 1 disk sitting on the start, and where do I want to move it? To the end. And I know the end is free because these n minus 1 are on the spare disk. So I'm now going to move the nth disk from start to end. Good. So I solve this, and now what do I want to do? I've got n minus 1 on the spare, and I want to move it to where? The end peg. Good. So solve that problem. Solve Hanoi n minus 1 from the spare to the end. Done. This is the power and the beauty of recursion. It seems like I'm cheating. I'm cheating. How am I defining the solution of this problem with complex rules by simply saying solve a simpler version of yourself? That's the power of recursion. Now let's convince ourselves that this actually works. All right, so here's my little code up here. Remember, move disk is just a print statement, and for purposes of space, I won't print that out here. So n equals 1, base case, you can just move the disk. If n is greater than 1, figure out what the spare disk is, solve two Towers of Hanoi with n minus 1, and then move the disk in between. All right, so let's walk through this and see how it works. Hanoi 3, 1, 2. I have 3 disks on peg 1. Please move them from 1 to 2. Good. How do I do that? Go into the code. Does the base case hold? Of course not. So what is the spare peg? In this case, the spare peg is 3. 6 minus 1 minus 2. So my job is to solve, sorry, I've abbreviated Hanoi here, and I think I did that for space. So Hanoi here should be solve Hanoi. I just did this because we're going to run out of space here. So move 3 from 1 to 2. I need to do 3 things. I need to move Hanoi 2 disks from 1 to 3, that's the spare. So 2 disks from here to here. Move the 3rd disks from 1 to 2, and then move 2 disks from what was the spare back to the original. And notice that I've written all 3 of these out here, okay, because that's these 3 lines of code. And all I've done is fill in the values for n minus 1, start, stop, and end. Now, what happens at this point? I've made a call to this function. That is a recursive call to this function. I'm going to expand that out in a second. But we can't forget that we have to come back. We're going to make this recursive call, which is going to lead to some more things. But when it's done, we have to come back and do this and then do this. So that nature of the recursive call is there is a promise to come back here when this is done being executed. But if this leads to another call, which leads to another call, you keep going down. And then when you're done, you come back and do this. It's sort of like the examples we've done with recursion before, where we build up this expression. So here we're not building up an expression, but we're building up a series of moves that we promise to get back to. Okay, so let's go ahead and start expanding this out. This is a recursive call, so let's go ahead and make it. So Hanoi of 2, 1, 3 says to solve, now start all over again, right? The start is 1, the end is 3, so the spare is 2. Your job is to solve a simpler problem, 1, from 1 to the spare. So that means move this disk from here to here. And then at that point, 2 is free to move to the end peg. So 2 moves here, and then I move 1 from 2 to 3. So these 3 steps are going to accomplish the following. I move 1 from 1 to 2. That's the current spare. I move 2 over to the end, and then I solve Hanoi 1, and I'm not expanding this out because that's eventually going to hit the base case, and so I just move it. So at this point, I have now completed this initial recursive call, which required another recursive call, a move, and another recursive call. But at this point, this function is now done. I will evaluate, and it is done. And now I'm free to move on to the next remembered command from the first call, which is to move 3 from 1 to 2. Good. And now I've sort of got to do it all over again. I've got to take these 2 disks, but now from 3 and move them to there. Well, how do I do that? Another set of recursive calls. Move the first disk from 3 to 1, move the second disk to the final disk, and then move back to there. So let's just go ahead and do that. So 1 moves from 3 to 1. I'm now free to move that disk, so I'm going to move it over. And then I do one more recursive call, which of course hits the base case, and then I am home. Good. So you can see in some ways here, I hope, the power of this recursion, that by thinking about solving this very complex problem with lots of different moves, and we'll talk in a second about how many moves there are because we've been doing a simple number of cases, and I thought about it as sort of recursively in terms of, well, if I can solve a simpler problem, how does that help me solve the bigger problem? So this is a very nice example. I think I would argue that the best iterative solutions won't be nearly so elegant and easy to implement, because this is literally the code that you need to do this, to solve this problem, and that's pretty nice. Now, I just mentioned the number of moves, and I want to sort of just talk about this very briefly, because it's a little bit of a hint of something that we will be talking about in 206B, and is really important when you are thinking about algorithms, whether they are recursive or iterative or whatever they are, which is, how expensive is this algorithm? So how much time is it going to take me to run? So let's just think about that little algorithm we just did. And there's ways of really formalizing this analysis that I'm going to do, but I'm going to do this sort of back of the envelope until we get to 206B. If I have one disk, how many moves do I have to make? Well, just one. I just move a disk from one peg to another. If I have two disks, how many moves do I have to make? Well, I've got to take one of the disks and put it onto the spare peg. That's one. I've got to then move the base over to the final, 2, and then I move the disk, the one that's on the spare back. That's 3 moves I've had to make. Okay, not too bad. Well, what about 3 disks? Well, for 3 disks, I've got to take 2 disks and move them onto a spare peg, slide one over, and then do it again. Well, how much does it cost me to move 2 disks? Well, 3. So if I've got to move 2 disks, that costs me 3. I move 1 disk over, that's 4, and then I've got to do another 3, that's 7. So notice for here, I sort of did it recursively. I didn't have to reanalyze, move a disk, move a disk, move a disk. I know that 2 of those disks are going to move over, and I know how much it costs me to move 2 of the disks. Okay, well, what about with 4 disks? Well, I've got to solve 2 versions of Towers of Hanoi with 3 disks, move 3 onto the spare, slide 1 over, move 3 back onto the resting spot. So that's going to be 7 plus 7 plus 1, 15. What are you noticing here? Every time I add a disk, how many more steps do I have to do? Double. I'm doubling, right? And plus 1. So 3 double is 6 plus 1. 7 double is 14 plus 1. 30 plus 1. 62 plus 1, and so on and so forth. That's a little scary, right? Because every time I increment by 1 here, I'm doubling my workload. Well, why? Why is it doubling? Well, think about the recursion. The recursion says in order to solve a problem with n disks, I've got to solve n minus 1 twice. Move n minus 1 to the spare, slide 1 over, that's the plus 1, move n minus 1. And so this is a very expensive computation, so that by the time you get to 64 disks, you have a very, very expensive computation that you are probably not going to want to do. And even with just 12 disks, you've gone from from 1 to 12, you've only added 12, but you've gone very rapidly. This is called exponential growth. And this is very, very bad for certain things. It's really good if something's expensive if you're trying to protect your password, like breaking encryption should be exponential growth. But if you're trying to actually solve a problem, exponential growth is a real problem, obviously. So I just love this Towers of Hanoi for 2 reasons. One is it shows really the power and the beauty of recursion, and it also gave me an excuse to show you what exponential growth is, which is something we'll be talking about down the line much, much more and much, much more formally. All right, that's it for recursion. A couple of things I want to say at the end of all of this. Don't get too confused. When I ask you to solve a problem, I will tell you if it's iterative recursion. And I don't expect you right now to know which is sort of the best. I just want you to be able to solve these problems thinking about them a little bit differently. But don't feel like just because recursion's weird, you have to solve all the problems with that, or you should avoid them. Like any design problem, you have to think about what is the best, most elegant, most efficient solution. And sometimes that will be recursive in nature, and sometimes it won't, and that's okay. Good. All right, so at this point, we're now ready to transition to object-oriented programming. So the next 3 full lectures are going to be classes and objects. And at this point, we really do have all of the scaffolding we need to be Python programmers. We have functions, we have variables, we have looping constructs, we have conditionals, we have return variables, we have parameters, we have recursion, of course. And now we're going to start thinking about data. Not just computation, but how do we store information and make good use of that data to solve interesting problems in efficient and elegant ways. And so when we pick it up, we're going to start sort of a new chapter, if you will, of this class, which are classes and objects. And then for the last 2 weeks, we'll talk about something a little bit different as well. All right, I'll see you in a little bit.